Index Partition, PIP, and the discovery of Pascal's dimensions, enabling computational retrieval and reversibility in high-index partition arrays.
The Polyhedral Index Partition (PIP) framework introduces an innovative approach to calculating integer partitions by leveraging the mathematical structures of Pascal's triangle, specifically through the concepts of Pascal's dimensions and Pascal's laterals. This paper explores the foundational principles underpinning PIP, elucidates the theoretical connections to combinatorial mathematics, and presents an efficient algorithm capable of handling large-scale partition computations. By integrating binomial coefficients and recursive methodologies, PIP offers significant performance improvements over traditional partition enumeration methods.
Author Andrew Lehti.
Table of contents.
Disciplines: cognitive psychology, linguistics, mathematics, and their histories.
Introduktion.
DOI 10.6084/M9, Figshare .276427883.
Theoretical foundations.
Date: November 9, 2024.
Pascal's dimensions and laterals. Foundations of Pascal's dimensions and laterals. Leveraging Pascal's triangle for direct partition calculation. Algorithmic Implementation. Conclusion. References. Erste Introduktion. Partitioning integers into distinct components is a fundamental problem in combinatorics. Traditional methods for calculating integer partitions often involve iterative enumeration, which becomes computationally prohibitive as the size and dimensionality of the partitions increase. This paper introduces the Polyhedral Index Partition (PIP) framework, which leverages the combinatorial properties of Pascal's triangle to compute partitions directly and efficiently. Central to this framework are the novel concepts of Pascal's dimensions and Pascal's laterals, which generalize the well-known binomial coefficients to higher dimensional partitioning systems. Zweiter theoretical foundations. Understanding the PIP framework requires a solid grasp of combinatorial mathematics, particularly binomial coefficients and their representation in Pascal's triangle. This section delves into the mathematical underpinnings that make PIP a robust and efficient method for partition calculation. 2. Januar Binomial coefficients and combinatorics. Binomial coefficients, denoted as nk, represent the number of ways to choose k elements from a set of n elements without regard to order. These coefficients are fundamental in combinatorics, appearing in various contexts such as probability, algebra, and geometry. 2. Februar Pascal's triangle. Pascal's triangle is a geometric representation of binomial coefficients arranged in a triangular format. Each row n of Pascal's triangle contains the coefficients n0, n1, nn. The triangle exhibits several key properties, including symmetry and recursive relationships, which are pivotal for efficient combinatorial calculations. 3. Pascal's dimensions and laterals. Pascal's dimensions and Pascal's laterals extend the principles of Pascal's triangle into higher dimensional spaces, providing a structured approach to partition calculations. 3. Januar Pascal's dimensions, generalizing rows of Pascal's triangle. Pascal's dimensions generalize the rows of Pascal's triangle to accommodate multidimensional partitioning. Each dimension corresponds to a specific combinatorial layer, allowing for the systematic calculation of partitions across multiple components. Dimensional growth. Dimension 1 represents single-element partitions, with constant values for each sum. Dimension 2 exhibits linear growth in the number of partitions. Dimension 3 shows quadratic growth, aligning with triangular numbers. 3. Februar Pascal's Laterals, subdivisions within dimensions. Within each Pascal dimension, Pascal's laterals represent subdivisions corresponding to specific contributions to partition sums. Defining laterals. Lateral 1, the leading diagonal, where all entries are 1, representing the simplest partitions. Lateral 2 captures partitions involving 2 elements. Lateral K, higher order partitions involving K components. 3. März observed patterns and symmetries. Pascal's dimensions and laterals reveal inherent symmetries and patterns that mirror the recursive nature of Pascal's triangle. Recognizing these patterns allows for optimization in partition calculations, reducing computational complexity. Lateral values across dimensions. To illustrate the relationship between dimensions and laterals, consider the following array of values, where each entry represents the number of combinations in each Pascal lateral across different Pascal dimensions. Dimension lateral 1, 2, 3, 4, 5, 6, 7, 8 von 1, 1, 1, 1, 1, 1, 1, 1. Tu 1, 2, 3, 4, 5, 6, 7, 8, 3, 1, 3, 6, 10, 15, 21, 28, 36 vor. The construction of Pascal's dimensions and laterals is grounded in fundamental mathematical principles, offering a unified way to understand partitions geometrically and combinatorially. 4. Januar Geometric Interpretation. Dimensional representation. Each Pascal dimension represents points in a hyperplane of fixed sum. For example, Dimension 2, points on a line x, y, where x plus y gleich n. Dimension 3, points on a plane x, y, z, where x plus y plus z gleich n. Dimension k, points in a k-dimensional simplex. Lateral contributions. Within these spaces, each Pascal lateral corresponds to a distinct layer of partition points, defined by combinations of sums at specific offsets. 4. Februar Combinatorial Basis. The mathematical basis of Pascal's dimensions and laterals lies in the recursive properties of binomial coefficients. nk gleich n1k1 plus n1k. This recurrence defines the growth of partitions across dimensions and their decomposition into laterals. Binomial coefficients and partitions. Dimensions represent sums of partitions using binomial coefficients directly. Laterals correspond to subsets of these sums, isolating contributions from specific partition elements. 4. Merz efficiency of calculation. The introduction of Pascal's dimensions and laterals transforms partition computation by avoiding iterative enumeration, directly calculating partition contributions for each lateral. Reducing computational complexity, leveraging the recursive structure of binomial coefficients. 4. April symmetry and optimization. Exploiting symmetry. By recognizing the symmetry in Pascal's dimensions and laterals, algorithms can simplify calculations, reusing results across partitions. Optimizing performance. The recursive nature of laterals allows for efficient caching and dynamic computation, minimizing redundant operations and enabling scalability to high dimensions. 4. Mathematical significance of Pascal's laterals. Pascal's laterals extend combinatorial principles to higher dimensions, deepening our understanding of partitions and their mathematical properties. They allow for systematic enumeration and computation of partitions in multidimensional contexts, reflecting the inherent combinatorial structures present in higher-order systems. 5. Leveraging Pascal's triangle for direct partition calculation. 5. Januar Theoretical Foundations, Pascal's triangle and binomial coefficients. Pascal's triangle is a combinatorial framework where each entry represents a binomial coefficient. It is constructed with a topmost entry of 1, and each subsequent entry equals the sum of the two entries directly above it. Formally, the entry at row n and column k is given by the binomial coefficient nk gleich n k nk. Key properties. Symmetry nk gleich nnk. Recurrence relation nk gleich n1k1 plus n1k. Row sums, the sum of entries in row n equals 2n. These properties underlie its use in integer partitions and binomial calculations. 5. Februar direct calculation of partition indices using Pascal's triangle. The algorithm introduced in section 6 relies on the principles of Pascal's triangle to directly calculate partition indices without iterative enumeration. This direct calculation approach offers significant performance improvements, especially when dealing with extremely large indices and high-dimensional partitions. Core concepts. Polyhedral indexing. The Polyhedral Index function computes the binomial coefficient x und y1 y, representing the number of ways to distribute x indistinguishable items into y distinguishable bins. This is derived from the combinatorial interpretation of Pascal's triangle. Approximation via binary search. The approximate function employs a binary search strategy to efficiently estimate the value of x such that x und y1 y n. This method leverages the monotonic growth of binomial coefficients to quickly converge on the desired value without exhaustive computation. Recursive partition calculation. The getPartition function recursively constructs the partition array by directly calculating each element using binomial coefficients, avoiding iterative enumeration. Inverse mapping. Functions like pair-inverse and inverse partition allow the algorithm to reverse the partition process, mapping a given partition array back to its original index. Exemple illustration. Consider partitioning integers from 0 to 14 into 3 parts without negative values. The partitions correspond to points in a three-dimensional space where each coordinate is a non-negative integer, and the sum of the coordinates equals a specific integer. 0, 0, 0, 0, 1, 1, 1, 0, 0, 2, 0, 1, 0, 3. 0, 0, 1. The bracketed counts, e.g., 1, 3, 6, correspond to the number of partitions for each sum, aligning with the third row of Pascal's triangle, y gleich 3, where the number of partitions for each sum n is given by n plus y1 y1. 5. März integration of Pascal's triangle in the algorithm. The algorithm intricately integrates Pascal's triangle through the following mechanisms. Binomial coefficient computation. Utilizing the npm binomial function from the math library, the algorithm accurately computes binomial coefficients, x und y1 y, directly leveraging the combinatorial properties of Pascal's triangle. Efficient search and approximation. The binary search within the approximate function efficiently navigates the numerical space, leveraging the predictable growth pattern of binomial coefficients derived from Pascal's triangle. This ensures rapid convergence to the desired index without iterative enumeration. Memoization for performance optimization. The @LR_cache decorator caches the results of binomial coefficient computations, preventing redundant calculations and significantly enhancing performance, especially for repeated or similar input values. Direct partition calculation. Instead of generating all possible partitions iteratively, the algorithm directly calculates each component of the partition array by systematically determining the appropriate binomial coefficients. This method reduces computational complexity and enables handling extremely large indices with minimal computational resources. 5. April eliminating iteration through mathematical insight. By harnessing the properties of binomial coefficients in figure-8 numbers, the algorithm eliminates the need for iterative enumeration of partitions. It directly calculates the desired partition array and its corresponding index through mathematical formulas, significantly reducing computational complexity and execution time. 5.4.1 Efficiency analysis for index computation. The Polyhedral Index Partition (PIP) method exhibits remarkable efficiency when computing index values, as compared to traditional methods. For an index value of 2, 255, 467 and 3 partitions. Traditional methods required Januar 2046 seconds to compute. The PIP method achieved the result in 0,00028 seconds. For an index value of 2, 25566 multiplicationszeichen 10, 20 and 16 partitions. Traditional methods estimated a computation time of 4, 5826 multiplicationszeichen 10, 21 years. The PIP method computed the result in 0,0699 seconds. These results emphasize the drastic efficiency improvements of the PIP method. 5. Mai Pascal's dimensions, accidental origins and observational discovery. The connection to Pascal's triangle and binomial coefficients was discovered by chance during recreational spreadsheet exercises. These exercises revealed triangular patterns that later became central to the algorithm. The significance of these patterns was not immediately understood, but their practical utility emerged as they were applied to algorithmic design. 5.5.1 Clarifying the accidental origins. This relationship emerged unintentionally. Experimentation with spreadsheets, aimed at developing a formula for prime numbers, led to the tabulation of row and column sums. Initially, these patterns were documented without a full understanding of their mathematical significance or recognition as Pascal's triangle, partly due to work involving higher dimensions and a modified structure. The relationship was nearly overlooked due to initial miscalculations. Only through manually generating the sums and correcting the errors did the accurate pattern become evident. The significance of these patterns became clear when they were integrated into the algorithm as shortcuts and lateral dimension markers, termed Pascal Laterals within each Pascal dimension. This integration revealed a strong alignment with Pascal's triangle. 5.5.2 The observed pattern. The pattern aligns with the sum of values directly above and to the left of each cell, representing the number of partition combinations across dimensions and laterals. This structure mirrors Pascal's triangle. 1 1 1 1 1 1 1 1 1 2 3 4 5 6 7 8 1 3 6 10 15 21 28 36 1 14 20 35 56 84 120. Each entry is the number of combinations in each Pascal lateral. For instance, row 1, single partition. Each entry represents one way to form sums. 0, 1, 2. Row 2, two partitions. Multiple combinations exist for sums, such as gleich 0, 0, 1 gleich 1, 1, 0 gleich 1, 0, 2 gleich 2, 1, 1 gleich 2. 2, 0 gleich 2, 0, 3 gleich 3, 1, 2 gleich 3, 2, 1 gleich 3. 3, 0 gleich 3. The sums and totals align with Pascal's triangle diagonals, revealing deeper mathematical connections. 6. Algorithmic Implementation. The PIP framework is operationalized through a Python implementation that efficiently computes partitions and their corresponding indices. The algorithm utilizes combinatorial mathematics, recursion, and optimization techniques to handle large-scale partitioning problems. 6. Januar Code Overview. Import sys from functools. Import LR_cache. Import empmat mpm sys z_max_str_digits 0 sys set-recursion limit 10.000 et LR_cache maxice gleich none def Polyhedral Index x y if x1 return 0. 6. Februar Detailed Code Explanation. Imports and initial setup. Sys module used to manipulate Python runtime environment settings. Sys z_int_max_str_digits 0 removes any limitations on the maximum number of digits in an integer string representation. Sys set-recursion limit 10.000 increases the recursion limit to allow deep recursive calls. Functools LR_cache decorator for caching function calls, improving performance. Math module, npm library for arbitrary precision arithmetic, essential for handling large numbers accurately. Erster Polyhedral Index, x, y. Calculates the number of ways to distribute x indistinguishable items into y distinguishable bins. X und y1 y. This function plays a crucial role in determining the cumulative counts of partitions up to a certain value. Caching uses it LR_cache to store results and avoid redundant calculations. Binomial coefficient computes the binomial coefficient with arbitrary precision using npm binomial. Zweiter Approximate n t x gleich 1 estimates the value of x such that Polyhedral Index x t n. Exponential Scaling multiplies x by 10 until Polyhedral Index x t n. Binary search refines x within a narrowed range to find the precise value. Dritter get pair, k. Computes the pair, a, b, corresponding to a given index k in a two-dimensional partition. Triangular numbers uses properties of triangular numbers and their inverses. Formula. N gleich 1 plus 1 plus 8k2. Partition components calculates individual components based on the index. Vierter get partition, n, y. Recursively computes the partition of an index n into y dimensions. Base cases handle scenarios where y is 2 or y gleich 2. Recursive decomposition breaks down the problem into smaller subproblems. Adjusting components ensures that the sum of components equals the desired value. Fünfter Partition, n, y gleich 2. Main function to compute the partition of index n into y dimensions. Setting precision, adjusts mpm mp dps based on the length of n for accuracy. Result conversion, returns the partition as a list. Sechster Pairverse, a, b. Calculates the index k corresponding to a given pair, a, b, in a two-dimensional partition. Cantor pairing function utilizes a formula similar to the Cantor pairing function. K gleich a plus b plus 1, 2 plus b. Siebter Inverse Partition, Stern a, and get inverse, Stern a. Reconstructs the index from a given partition tuple. Recursive mapping builds up the index by summing cumulative counts. Base case uses pair inverse when only two components remain. Sechster März main execution. Setting n and p defines the index and number of partitions. Computing the partition calls partition n p to obtain the partition tuple e. Verification prints the partition and the computed index to confirm consistency. Siebter Conclusion. The Polyhedral Index Partition (PIP) framework presents a significant advancement in the calculation of integer partitions by harnessing the combinatorial properties of Pascal's triangle through Pascal's dimensions and laterals. By moving beyond iterative enumeration and employing binomial coefficients in a multidimensional context, PIP achieves remarkable efficiency, enabling the handling of extremely large indices and high-dimensional partitions with minimal computational resources. The integration of recursive algorithms, memoization, and arbitrary precision arithmetic further enhances its practicality and scalability. The accidental discovery of the underlying patterns during exploratory exercises underscores the serendipitous nature of mathematical innovation. The formalization of these patterns into Pascal's dimensions and laterals not only provides a robust theoretical foundation but also translates into tangible computational benefits. As demonstrated, PIP outperforms traditional methods by orders of magnitude. Future work may explore the extension of PIP to even higher dimensions and the exploration of further mathematical structures that can enhance partition calculations. The PIP framework stands as a testament to the enduring relevance of classical combinatorial principles in modern computational challenges. Achter References. Pascal, B. 1654. Traité du triangle arithmétique. Paris, Schätzjacke Savary. Cantor, G. 1891. Contributions to the Founding of the Theory of Transfinite Numbers. Mathematische Annalen. Rosen, K.H. 2007. Discrete Mathematics and its Applications. McGraw-Hill. Graham, R.L., Knut, D.E. und Pataschnik, O. 1989. Concrete Mathematics. Addison Wesley. Stanley, R.P. 1999. Enumerative Combinatorics. Cambridge University Press. Sloane, N.J.A. 2003. The Online Encyclopedia of Integer Sequences. Available at OEAS.